Today's title is What is Important About Quantified Boolean Formulas? And this is a talk by myself, Leroy Chu. So with this title, there's this word important, and this is kind of a misnomer, because this is not going to be a talk about exactly what are the most important things that arise from quantified Boolean formulas. Instead, this is really going to be a talk about comparing quantified Boolean formulas with other objects such as propositional logic. The reason why I've used the word important is because if I use some sort of title that said what is different about quantified Boolean formulas, it implies that it is different to something else. And I think I do not want to assume that my audience know what I'm talking about when I'm talking about different. So I'm here going to use the word important. And we're going to see its importance within a particular framework. So we're going to look at its importance to me, in fact, in my area, which is proof complexity. So here's a little map about various topics around proof complexity. So on the left, we have the complexity classes. The complexity classes are sort of the cornerstone of theoretical computer science. And that has a relation to proof complexity. Proof complexity also has a relation to practical logic solving. And this is sort of the main theoretical framework of logic solving. And finally, something that's close to me is the connection from circuit complexity to proof complexity. Although really this is a conjectured connection from circuit complexity to proof complexity, as a lot of what is there has not yet been shown, but we'll see in this talk that we get there somewhat. So we're going to be moving basically from left to right in this talk, but it's actually these arrows really that we'll be examining. So let's start off. We start off with complexity classes. So the first class that we'll introduce is the class P. P is the class of all languages L, where this L can be decided by a deterministic Turing machine, DTM, in polynomial time. So that means if we put an input into this machine, it will tell us in polynomially many steps whether this input is a member of this language. So each language will have its own machine. So this is the class of polynomial time computable languages that are decision languages. NP is the class of all languages which can be accepted in polynomial time using a non-deterministic Turing machine. So that's a Turing machine where the steps don't tell you exactly which configuration you're going to end up in next. And then finally we have p-space. So p-space is again using deterministic Turing machines. However, instead of looking at the number of steps like we did in P, we look at the number of memory cells that we're using. So this is a measure of memory, and at the end we've got this comparison. So P is also, anything in P is also included in NP, and that's because non-deterministic Turing machines encompass all deterministic Turing machines as well. And then we have P is also a member of p-space because the number of cells that we use, well, in order to write to that cell, we need to use a step. So the number of steps is in fact a strict upper bound to the number of cells that we can use. The relation, the final relation that I've not talked about is that NP is contained in p-space, and that's a bit more complicated, and we'll leave that. So when talking about complexity classes, it's inevitable that we talk about hardness and completeness. A language is NP hard if every NP language can be effectively transformed or reduced in polynomial time to that language. And NP completeness is if and only if it is both NP hard and in NP. Similarly, for p-space, we have p-space hardness when we can transform every p-space language into that language, and p-space completeness when that language is also in p-space. Now we move on to proof systems, which relates to this proof complexity topic. A proof system is a partial function that maps proofs to theorems. Okay, so that's the framework we're going to be using. And formally we defined it from strings to strings. There's three conditions for a proof system. So the first is verifiability. So in some sense, you want your proofs to be sort of obvious. You want the steps to be laid out in front of you. And so we kind of want that it's easy to check. So that condition translates to f being computable in what computer scientists agree is easy to check, which is polynomial time. The other conditions are soundness. Soundness is very important because it means that every theorem that we have a proof for must be correct. It must be in our language. And completeness, if we have a proof system, we want it to be complete for that language, which means that every theorem in that language has some proof. So what do proof systems get us? Well, it gives us an alternative definition of NP. If we have a language where we have a proof system where every theorem has a polynomially bounded proof, then that language is in fact in NP. And that is an if and only if. So this gives us this alternative definition to NP, this polynomially bounded proof or witness. So going back to NP completeness, let's talk about our first example of an NP complete language. And this is an example of SAT. So a propositional formula, so that's a formula using the usual propositional connectives and using variables which represent either true or false, but no quantifiers. So this propositional formula is said to be satisfiable if and only if it is true under at least one true-false assignment to the variables. SAT, which is the satisfiability problem, is in the class NP because what we can do is if we have that formula and have an assignment to that formula, we can check in polynomial time whether this is satisfiable, and so this counts as a polynomially bounded proof. That gives SAT being in NP. SAT is also NP hard. So, and this was proven by Cook in his famous theorem. So the idea behind SAT being NP hard is that we take Turing machines from each language in NP and we transform them into SAT formulas. Okay, so each language in NP can be solved by some non-deterministic Turing machine in polynomial time and space. So what we do is we create variables, and these variables sketch out the memory configuration of the machine. So we have variables for the values of the tape, we have variables for the one of the finite states that the Turing machine is in, and variables for wherever the position of the read-write head is. And we copy those variables for every possible time. But there's only polynomially many times as well. Then what we do is we have some sort of propositional formula that tells us whether we can get from one configuration to another configuration in a single step. We also add to that our output state, which is saying that we want to have some sort of acceptance. And so this formula is only satisfiable if we can get from the initial state, the initial configuration, to our accept configuration. And this assignment corresponds to the non-deterministic choices in that machine. Okay, so why does this make SAT important? Well, if we look at many different NP problems, so here we've got some examples of problems in NP, normally what you do is that researchers would investigate different algorithms for each of these problems. and then find a solution. And each of these algorithms would be optimized independently. Instead, what we could do is we could just take all that energy of research and just put it into making the best possible SAT solver. And why is this a sensible idea? Well, what we could do is we know that we can convert these NP problems in polynomial time into the SAT problem. And then if we just use our best SAT solver, we can then solve it at the rate of our best SAT solver. So it also means that when we optimize the SAT solver, we're optimizing all these problems uniformly. And what do these SAT solvers look like? Well, the modern SAT solvers are based on a DPLL algorithm and an improvement known as CDCL. The next slide, well, this slide, is the DPLL algorithm. So what we do is we have a function for DPLL, and this picks some branching variable that's not assigned in our formulas, and then sets it to either 0 or sets it to 1, and then performs DPLL again, and then returns corresponding to, if we have found a satisfying assignment, then this satisfying assignment backtracks to this thing here. At the base case, well, we're simplifying, so if we find a contradiction, or if we find that this formula is satisfiable, then we just return our thing here. Okay. In practice, we had some improvements for DPLL. So first of all, what we can do is we can pre-process. And that means we have some sort of propositional formula, and we just change it to an equisatisfiable propositional formula, and maybe this equisatisfiable propositional formula might be easier to run on our DPLL algorithm. I've sort of cheated. I've just had this the sub-procedure simplify, and the simplify can be sort of adjusted to include more and more advanced reasoning. Another thing that I've been sketchy on is this step here. It says pick A as any variable, but in fact which variable you pick alters the running time of the DPLL algorithm. And so using a good heuristic to pick the pivot literal is crucial for having a well-performing SAT algorithm. Another problem is that you, as well as running time, might be memory. You don't want to run out of memory. And so what you can do is you can create data structures. In particular, these data structures just have to preserve this satisfiability. So you can be a bit lazy and have lazy data structures, and this can be used to save memory, which is very important. So the big improvement on DPLL algorithm is the CDCL algorithm for conflict-driven clause learning. And that is what we do is when we get to a point where we find a contradiction, we find something is unsatisfiable, we use that to learn some sort of logical information and conjunct it to our original formula. And this allows us to do something called non-chronological backtracking. So normally we just backtrack up by just this one variable, but we could go further back to a state, but using the but keeping this learnt clause, and we could go as far back as to restart. So modern CDCL solvers are in fact very successful. I should mention this, and so it can do something like millions of variables. Okay. So you can't really talk about satisfiability without also talking about unsatisfiability. And you can't really talk about unsatisfiability without talking about tout. So tout is the language of propositional tautologies. And basically, when you're talking about propositional tautologies, you're really talking about unsatisfiable formulas, because a propositional formula is a tautology if and only if its negation is unsatisfiable. There's no satisfying assignment. there's this complexity class CoNP. So CoNP is the class of languages where the complements of those languages are in NP. So tout, being the same as unsatisfiability, is CoNP, and it's also CoNP complete. And this gives us to a sort of hand-wavy thought, and that is, we can think of NP as having this existential element. We have to have this proof existing. And dually, if we think of CoNP languages, we can think under all inputs of a certain size, we always get this result. Tout, in fact, has a polynomially bounded system if and only if NP equals CoNP. So P versus NP is a famous problem. There's also unknown whether NP equals CoNP, which is in fact a weaker claim. So now we move on to resolution, and we're looking at resolution because it is a first example of a proof system for propositional logic. Particularly, it's a proof system for unsatisfiability. So we're trying to arrive at a contradiction. And it operates on conjunctive normal form propositions. What does that mean? It means that at our lowest level, we're looking at propositional atoms, propositional variables. And the next level is where we can introduce a negation, and that gives us something called a literal. So literals are either propositional variables or negations of propositional variables. Then then the next level we have disjunctions, which gives us clauses, and then finally conjunctions, which gives us CNFs, conjunctive normal form. Resolution only has one rule, and this rule here takes two clauses, merges them together, but has this crucial pivot x, where x appears positively here and negatively here, and it removes these two literals, these two x literals. Resolution is in fact connected to CDCL. If we have a formula and the minimum proof size is available for that formula, that minimum proof size is in fact a lower bound for the solving time. And in fact, DPLL has the same relationship to a tree-like resolution. So what can we say about these minimum proof sizes? Well, there are in fact formulas where the minimum proof size is in fact exponential. And the idea behind these lower bounds are that they come from combinatorial theorems. So you can use something like the pigeonhole principle, or use the fact that a graph cannot be k-1 colorable and have a k-clique. And these contradictions can be coded into propositional logic. And for some reason, resolution is not very good at doing things combinatorially, like counting. So you get some sort of lower bound where these proofs are required to have at least exponential size. So now we look at a strong proof system where we don't have these problems, and this is extended resolution. And I've picked extended resolution deliberately because it's quite an easy improvement over resolution. So extended resolution includes the extra rule, the extension rule, where we can introduce a new variable, okay, a variable that we haven't seen before. And this variable represents here the NAND, the not AND of two existing variables, x and y. This can be introduced in clauses. Because not AND is functionally complete, you can basically say that we can introduce variables for any sort of function, because we can, once v is an existing variable, we can then build more extension variables on top of that to compute any function. And well, the bad news is that extended resolution doesn't really correspond to any known solvers. It's a bit too powerful. It doesn't really tell us anything. The good news is that it sort of captures a lot of things, and there are no super polynomial lower bounds that we know of for extended resolution. So I've concluded my section on propositional logic. So now I want to move on to the main topic, which is quantified Boolean formulas, which we shorten to QBF. So what are QBFs? Well, they have propositional connectives, propositional variables, which are Boolean, so they range over true and false, and they also introduce some quantification. There are Boolean quantifiers, the universal quantifier for all, and the existential quantifier exists. And the range of these quantifiers are over 0 and 1. And they bound propositional variables. Okay, so here we're saying for all values of this x variable here, which can only be 0, 1, there exists a 0, 1 value of y such that x if and only if y. And this is an example of something that is true, because for each x, whether it's 0 or 1, there exists some value in 0 or 1 for y such that y equals x. So QBFs don't really express anything that propositional logic can't, and in fact they're shorthands for connectives. So exists is some way of doing disjunction over 0, 1, and for all is some way of doing conjunction over 0 and 1. So here's the example again. Here we have that this innermost formula, there exists y for all, there exists y, x if and only if y, is the same as saying, well, either having y0 or having y1, one of these things is true. And then this for all x is a conjunction, so we plug in 0 for x here and 1 for x here. And here's the conjunction. And since all our variables were bound and we've expanded out all these variables, we've now just got a formula with constants in them, and we can easily evaluate this, and it tells us that this thing is true. So yeah, QBFs don't express anything more that propositional logic can't, but it does give us perhaps a way to write formulas more succinctly. And in fact, we might see something like that because QBF is p-space hard. So here we're going to prove it. If we have some p-space problem, well, what do we know? We know there's going to be a deterministic Turing machine that decides that problem. And that deterministic Turing machine only uses polynomially many cells. It might use more than polynomial amount of steps, but we know the cells. So we now look at a number of possible memory configurations that we would use on these cells. And this is bounded above exponentially by m, which is of the same magnitude as our polynomial. So what's our idea? Well, what we're going to do is we're going to create a QBF that describes reachability from different memory configurations. So here we have that C2 is a memory configuration that is reachable from C1 in the path length of 2 to the I. So our base case will be just something that includes one step, and for there we can use the translation we did for Cook's theorem for SAT. More interestingly is the inductive step, is where we start using our QBF machinery. So what we do is we say we use the induction hypothesis here, but we talk about the existence of a middle state, middle configuration, C3, and we have these other things, D1 and D2. What do D1 and D2 do? If D1 equals C1 and D2 equals C3, then we trigger this. And if D1 equals C3 and D2 equals C2, then we trigger this thing. The idea here is that we want to create a formula, but we do not want this formula to inductively grow at a super polynomial rate. So using these quantifiers here, we ensure that this thing is succinct. And then for the final state, we just put in the input and the output, which is our accept state, and this gives us a polynomial size QBF, which is true if and only if x is in our language. Okay, so what do we do when we solve QBFs? Well, we have a QDPLL algorithm, and it works much the same as a DPLL algorithm. However, once you pick your literal, you do a different thing depending on whether it's universal or existential. So here, if it's universal, it becomes 0, you return 0. If it's existential and it's 1, you return 1. And if neither of those things, you just try the literal and the opposite value. So it's quite similar. However, this literal has to be picked in the outermost blocks of the prefix. So QDPLL is a p-space algorithm, and there is a version of QCDCL that improves upon it. Deciding QBF is therefore p-space complete because it is both in p-space and is p-space hard. The other important thing about QBF that relates it to complexity classes is that it has a relationship to the polynomial hierarchy. So I won't really describe what the polynomial hierarchy is, but the idea is that we get there from QBF by restricting alternations to a certain type of prefix. So if we want to talk about pi p1, which is np, we just have existential quantifiers. Similarly for pi p2, we're talking about universal quantifiers. We could do different alternations to get us into areas where we're talking about different complexity classes. And these are not just only in these complexity classes. Having these restrictions gives us complete languages for the polynomial hierarchy. Finally, we're going to talk about an alternative definition to QBF. And I say finally, as in finally for the introduction to QBF, we will be talking more about QBF. We can see QBFs as some sort of game. So we consider a QBF in prenix form. So prenix form means that we put all the quantification on the left. And that's easy to do. And we're only considering conjunctive normal form QBFs. In fact, we don't, for this semantics, it doesn't need to be conjunctive normal form. A QBF represents this two-player game between the players existential and universal. And what happens is you move from left to right on this prefix. Each turn is a variable, and that variable is set by whoever's variable it is. So this variable y1 will be set by universal, and once we get, then we'll move on to y2, it's also set by universal. Then we get on to x1, which is set by the existential player. The existential player is in fact trying to make this propositional matrix become true, while the universal player is trying to do the opposite. And it turns out that a QBF is true if and only if there exists a winning strategy for the existential player. And it's false if and only if there's a winning strategy for the universal player. So here's an example. And we can verify that this example is true by demonstrating a winning strategy for the existential player. So on the first turn, the universal player will always play u to some value. And the idea is is playing the opposite value for E will always guarantee that our formula here is true. So now we can talk a bit about QBF applications. So this goes back to my title, why is QBF important? Well, the universal quantification means that QBF can be used for things where that universal quantification is useful, and something like formal verification is an example of that. So formal verification is typically done now on hardware, but you can use it to verify anything, but hardware is its modern use. We also described that QBFs capture the polynomial hierarchy, which means any sort of problem, such as AI problems, that fall upon the polynomial hierarchy can be captured by QBF. So here's abstract argumentation, minimal entailment. And then finally we have this game semantics, which means that we can talk about games using QBFs. We can convert games to QBFs. So examples of games, so sort of typical board games like chess, although you have to be careful about the number of terms. You don't want to have unbounded prefixes. Probably a more cleaner example is Super Mario Bros, because you have a time limit on that. So that gives us these bounded prefixes. But that, despite being arguably more complicated than chess, that is also within P space and can be represented by QBF. So now we move on to QBF proof systems, and we're edging closer and closer to QBF proof complexity, which is my topic. So the QBF proof system that we're going to see, or the weak QBF proof system we're going to see first, is QU resolution. So this has two rules. The first rule is a resolution rule, which is still sound when dealing with QBFs. Secondly, we have the universal reduction rule. And how does this universal reduction rule work? Well, what it does is it drops universal literals, but only under a certain condition. This condition is that whenever we have a clause, we look at all the literals in those clauses and each of their variables, and we check where those variables are in the quantifier prefix. We make sure that the variable corresponding to this literal k is the innermost of all the variables that we're looking at. And that allows us just to drop k. So one condition on universal reduction is that when we have tautologies, we're not allowed to reduce one of these literals here. It creates problems. So in general, we just sort of disallow tautologies because they're kind of useless anyway. There's two versions of QU resolution. There's a tree-like version where lines can only be used once after you derive them. Once you use them, you have to re-derive them again from the axiom. The typical QU resolution that we talk about is the DAG-like version of QU resolution. Once we derive a line, we can reuse it as many times as we like. So going back again to this for all reduction, we'd like to verify its soundness. And here's a little argument for why it's sound. So what you do is you look at some sort of QBF where in our propositional matrix we have just the matrix and a clause containing this variable u. And we have that C only contains variables in this pi1 part of the prefix. Okay, so nothing is from C is quantified more inner than this u. What we can do is, once we've got this formula, we can expand out this u. So that gives us a conjunction of these two sub-QBFs. Notice here that we have to change the variables, but this doesn't really matter. Once we do that, we can simplify this thing. So this 0 disappears. Having or 0 is useless. So it just disappears. Having or one makes this thing a tautology, and having and a tautology is useless, so we can remove that. Then what we do is we just we can put C here again because it doesn't contain any of these variables, and then we can just stitch this back up again using a universal variable, and we might as well just use U again. Okay, so here's an example of QU resolution. So here we have our QBF, and we want to show that this thing is false. So what we could do is we could do a resolution step on the variable, the existential variable E. We end up with this clause here, U. It would be U or U, but that simplifies just to U. And then with this thing, we can just do a universal reduction. We get the empty clause. Right, so we've looked at a weak QBF system. Now let's look at a stronger one. So this stronger one is extended QU resolution. So the weak system resolution corresponds to QU res, and then we've got extended res that gives us extended QU res. And so here all we do is we add the extension rule. However, we have to be careful because we introduce a fresh variable. This fresh variable needs to have some sort of quantification. Okay, so first of all, what kind of quantification, and then where does that quantification fall within our prefix? So the first question is easy. We just always do it existentially when we're dealing with false formulas. The second idea, well, there's two possible answers. Either the safe way is to just put it at the end, and that always works. But it also turns out to be safe in general if you just put it after the variables it depends on. And that's in fact the better way of doing it and how we do it. So now that we've introduced the proof systems, we might want to look at lower bounds. Okay, and it turns out that if we have lower bounds from propositional logic, so for example lower bounds for resolution, these are also lower bounds for QU resolution. Likewise, any lower bounds for an extended resolution would become extended QU resolution lower bounds, but we do not have any of these yet. And this is not very interesting. It misses the point. We should have sort of additional hardness in QBF, and we want to really find that. So one new way of looking at this and getting rid of this effect is to actually use NP oracles or co-NP oracles, because they're the same thing. And it sort of introduces a new rule where we're allowed to introduce propositional tautologies. Introducing propositional tautologies is not really a valid step in a proof system unless NP equals co-NP. However, this is just some sort of framework that we can use to help us find genuine QBF lower bounds. So then how do we find QBF lower bounds? Well, the obvious thing to do is to look at the ways of finding lower bounds for propositional proof complexity and lift those ideas to QBF, sort of generalize them. There's another thing here, and this is something we'll come on to later. It's a successful way of getting QBF lower bounds is using circuit complexity. Right. But first of all, we'll just look at the lifter techniques. So the first lifter technique is the asymmetric prover-delayer game. And what you do is you have a game and the two players end up constructing some sort of branch of this proof. But in doing so, they take into account the other branches coming out of that branch, and it turns out that the score of the game is proportional to the logarithm of the proof size. And this asymmetric prover-delayer game also works for the tree-like version of QU res, and you can use that characterization to find a lower bound from this paper, which is conjectured to be hard for QBF proof systems, and it is hard for tree-like QU resolution. Another technique is from propositional logic is feasible interpolation. If we have an implication, A implies B, there is some C where A implies C and C implies B, such that C is only in the joint variables of A and B. If we have some sort of circuit complexity lower bounds for C, we can use that to generate proof complexity lower bounds. And this can be used to show lower bounds for clique versus color formulas for propositional logic. You have to change things a bit when moving up to QBF. These are no longer propositions, but you can make more formulas than you could before, and you can do something like clique versus having no clique in a graph. And this is another source of hardness that is genuine QBF hardness. Finally, we talk about the size-width relation because we didn't find much success in this. It's an unliftable technique. So width is the size of the largest clause, the number of literals in that clause. And the minimum width has been shown to be basically the logarithm of the minimum size. And this is really sort of the main technique for resolution lower bounds. However, this doesn't really seem to work in general for QBFs. Okay, so now we move on to this other idea, using circuit complexity lower bounds. So there's a bit of that in feasible interpolation, but I think the stuff in QBF goes a bit further than that. But to talk about it, I have to introduce some very basic concepts of circuit complexity. So circuit complexity deals with circuits, and what are circuits? Well, circuits are basically DAG-like formulas. Formulas have sort of a syntax tree, which is a tree, and circuits allow you to have DAGs. So you could, in theory, you could be saving circuitry by making it into a DAG. And circuit complexity concerns itself with this question. Do we have some sort of family of, can this family of functions be found with a family of circuits such that a measure in that family of circuits is bounded by some growth function? So a clear example of this, so the obvious first thing to do is P/poly, which is the class of functions where these circuits are bounded above by polynomials. Another one is AC0, where these functions are bounded above by polynomials, but also the depth is constant. And AC0 has a lower bound, so parity, which measures how many of your inputs are 1, and if it's even returns 0, if it's odd returns 1. That function is hard for AC0. So how does this become a lower bound technique? Well, what we do is we exploit the strategies in the two-player game, so the two-player semantic game. If we recall, every false QBF has a winning strategy for the universal player. And the idea is that if we can somehow turn hard strategies into large proofs, then we only need to find false formulas with hard strategies for the universal players. The contrapositive of this is that we just find a way of getting easy strategies from short proofs. And this leads to strategy extraction. This is something that was already known. If we have a QU resolution proof, we can extract from that a short strategy for the universal player in this particular format, decision lists. And we'll see that decision lists are in fact these decision lists can be expressed as bounded depth circuits, AC0 circuits. So this is what a decision list looks like. It's a chain of if then else. It just continues until we reach some sort of endpoint here. And the if conditions are conjunctions of literals, so terms. And a decision list can be transformed into a circuit of depth 2. And the way you do it is you have all the knots of each of these terms And if the condition is there, then you get the output. We have a disjunction of these things for the value 1. So we have to do the second part. We have to have QBFs where we have hard strategies. And to do this, we can take any Boolean function, and we have this QBF QF, where we have existential for the input. We have some universal variable here, z, and then we have some auxiliary variables, and we say that z has to be not the function on these input variables. The way we code this function is using these auxiliary variables. So they describe the computational circuit for this. Having z not equal to f means that the only winning strategy for the universal player is to play z equal to f. And we can do this thing for parity, and this gives us Q parity. So how does this all come together? Well, if you have short proofs, via strategy extraction, we always get short strategies. If you have long proofs, well, we can either have short strategies or long strategies. But the key here is that long strategies could only come from long proofs. So if we have parity, which must be large in AC0, then Q parity in QU resolution must have long proofs, must only have long proofs. Therefore, Q parity is an exponential lower bound for QU resolution. So now we move on to looking at extended QU resolution. What can we do there? Well, extended QU resolution proofs are kind of just the same as QU resolution proofs. If we just do all our extension steps done right at the beginning, it doesn't really make a difference to the soundness of our proof. So we just do them all in advance, and then the format of this thing is much the same as QU proofs, and so we can you can get decision lists, extract them in polynomial time. The caveat is that the variables used in this decision list aren't only the original variables, they also include the extension variables. But you can remove these extension variables and replace them with circuits that compute the functions that these extension variables represent using polynomial size circuits, p/poly circuits. And the whole thing itself, the decision list, which has p/poly circuits within it, is a p/poly circuit. And this gives us p/poly strategy extraction for extended QU resolution proofs, which gives us some conditional lower bounds. So it means if there's a function that can be expressed as a QBF, so that's what I mean by being in P space, but is not computable in p/poly, then the Q of that function is a lower bound in extended QU resolution. And we can examine the converse. So what do I mean by that? Well, I mean that the converse isn't exactly the same. It isn't exactly true, but something similar to the converse is in fact true. So the way we approach that is via something called formalized strategy extraction. So consider this idea. Consider that we already have the strategies for each of the universal variables in the false QBF, so some sort of circuit that computes these strategies. If we replace them, if we replace those universal variables within the matrix with those strategies, then the matrix here with those variables replaced, here, must be, it's just propositional if we just ignore these quantifiers, and it must be unsatisfiable. This universal player is playing so that this thing is always false. So this idea gives us a way of getting a normal form for extended QU resolution proofs. And what happens in this normal form is, first of all, we get these strategies. We extract them. We derive, using extended resolution, that this, so just using propositional rules, that yi cannot equal this thing here. We start with this matrix here, and a propositional conclusion of that is this thing here. These yi's cannot equal the strategies, otherwise we'd get false. Once we've got there, then we can start using our universal reduction. And inductively what we do is remove this innermost yn. So we can reduce that in both 0 and for 1. And it means this thing somehow has to end up being 0 and 1, which is impossible. We end up removing this term and inductively proceeding until we've got the empty disjunction, which can't be satisfied, so it's false. What does this give us? It gives us a characterization for extended QU resolution. So QU resolution only has a lower bound if either extended resolution has a lower bound, or we can find some function that is in P space but not in P/poly. And the backwards direction is the easy direction. We've already discussed this point here, and this point is just lifting extended resolution lower bounds. These are also extended QU resolution lower bounds. We just existentially quantify. The forward direction, this is where we use the normal form. Suppose we have some formula which is a lower bound, so it must require superpolynomial proofs. We take the shortest refutation must be superpolynomial, and we convert it to normal form, which must also be superpolynomial. This means that either this proposition requires a long proof from phi, which shows a propositional lower bound, or the extracted strategies must be incredibly large, which actually gives us a circuit lower bound. So that's how we prove this thing here. There's quite a big significance from this result. One thing is, based on some things from propositional logic, it means that every QBF proof system with strategy extraction in P/poly, it can be P-simulated, so it can be effectively, this proof system can do everything that the P-simulated proof system can do. So extended QU resolution, so it's P-simulated by extended QU resolution plus this thing here, where this thing is just a bunch of polynomially recognized propositional formulas. And this, I think, is quite powerful because it's just saying this thing is doing most of the work, most of the QBF stuff, and we might only need to add some propositional stuff in order to do it. Another way of saying this is that among all the QBF proof systems with P/poly strategy extraction, extended QU resolution with an MP oracle is in fact optimal. Okay, I'll talk a bit about Frege systems because there are people that are more familiar with Frege systems. But I'll just introduce it briefly. It's just textbook style systems with complete rules of inferences and axioms. So probably the first proof system you ever saw was probably a Frege proof system. We denote C Frege, where C refers to the complexity of the line. So example is P/poly Frege is where our lines are circuits, and this is in fact equivalent to extended resolution. P/poly Frege, once we add a Fourier reduction rule, is in fact equivalent to extended QU resolution. Frege with NC1 lines, so lines that are formulas, is similar. If we add the reduction rule, it's similarly characterized by NC1 lower bounds, just like this thing here. We just replace this P/poly with NC1 and these things correspondingly with the Frege systems. Another important thing is that AC0 mod P Frege doesn't have any known lower bounds, but if we look at the QBF version with Fourier reduction, we have lower bounds from strategy extraction. Q parity is an example of something that is hard when P is not even. Finally, I'm going to talk about sequent calculi. So I'm just talking about this because people are familiar with sequent calculi as well, but it's also important. So the sequent calculus has all the propositional rules, and it has some 4 extra rules to deal with quantification. And the sequent calculus G, well, it simulates extended QU resolution. But it avoids strategy extraction. It does not have strategy extraction unless P equals P space. And doing so, it avoids this lower bound technique. So in fact, it should make it stronger unless P equals P space. So how does this whole theoretical look into QBF affect practice? Well, strategy extraction is something that is considered beneficial in solvers. If you have a chess instance and you convert it into QBF, you want to know the strategy because that strategy corresponds to how you should play chess. However, in some sense, strategy extraction is harmful. It affects the proof size because we could have formulas where the only strategies are hard, and that corresponds to proof size lower bounds, which also means it corresponds to running time lower bounds when we're looking at solvers. So, I mean, I have some sort of idea that what we should be doing is we have some certain solvers which can turn strategy extraction off. And in certain scenarios, this might work to our benefit. However, QBF solvers aren't up to that yet. They're nowhere near as powerful as even the proof systems, like QU resolution. And this is because going back to QDPLL, we saw that you could only choose a variable from this outermost block. And that makes all the difference because there's none of that restriction when dealing with QU resolution. Okay, you can resolve on any variable. Yeah, so there's some sort of work in trying to get QBF solvers up to speed. Some ideas include dependency schemes. So dependency is some way of violating that order by showing that it doesn't really matter. The variable that appears to the left of the variable you're considering might be independent. So you might be able to jump ahead and do that first. Another thing you can do is there's a completely different approach in QDPLL, and that's using universal expansion. So it's using the idea that you can take a universal variable and expand it both to 0 and 1. You end up with an AND, but that's fine because it just introduces more clauses. And then if you can do that for all the variables, you can treat your formula as just a SAT instance. So that's another approach. And in fact, I think that approach is doing better. With these approaches, dependency schemes and universal expansions, we do have proof systems that capture these ideas, and these have been looked at. But that's beyond the scope of my talk, and in fact, my talk is finished.